Let's take another look at divide and conquer algorithms with a simple problem that comes up on the likes of LeetCode or HackerRank or other basically coding challenge sites. So it's LeetCode calls it two-sum. So you take an array or a list of however many values, and you look for two of them that add up to a given target. Really, a naive implementation of this is really easy in OCaml. I'm going to write it right now with a recursive function that looks for a target, and it's going to say, okay, if the pattern match on that list, if it's empty or it just has one element, which we don't need to give a name to. Obviously, nothing was there, so we're going to raise the standard not found exception. If there is, though, I'm going to pattern match on the first element and the tail of the list and say that if we find the first, or rather I should say the complement, so that target minus the current value in the tail, then we can return that value and the target and the complement. Otherwise, we're going to run the function recursively and look for that target in the tail of the list. Very easy. And if we try an example of this, we say we're looking for 7 in a short list. Very quick answer. We're going to get 2 and 5 because those add up to 7. The problem is, when you look at how this works, we worked with a really short list, 7 items. It didn't have, so it starts with 9 and it says, okay, the complement of that to get 7 would be -2. It scans through 8, 2, 4, 5, 1, 6 and doesn't find -2, so it continues on and says, okay, 8, does it find a -1 in that tail of that list? No. 2, yes it does. Done. That's a short list. If the list were much longer, it would take a lot longer time. So I'm going to just quickly, the @ is going to apply the next thing. It's just basically a way of getting rid of some parentheses here. So if I make myself a list of 100 random numbers and look for that, still ran pretty darn quick. Let's try 1,000. Still pretty quick. So, 10,000. Oh, not found, but it took a lot longer. Now, that's the largest size list that something like LeetCode would test you with, because our quadratic complexity equation, so multiply 10,000 by 10,000, you get 100 million. So now we're doing 50 million comparisons. I'm going to be a lot meaner than LeetCode is, and I'm going to say a random list of 10 million items. I'm going to see how long that takes, but I'm going to get bored before this finishes. So we're going to start on a slightly different approach. What we need is an easier way, a quicker way to find elements in a collection. And that means we can't just go through a list because a list is linear. To scan it, we have to look at everything in it every time. If we had a binary tree, though, and specifically a binary search tree where everything to one side of the tree there's a root value, everything to the left is smaller, everything to the right is bigger, we can very quickly narrow down on whether a particular number is in that tree. So such a tree obviously has the option of being empty. There could be nothing in it. Or we look at a node. Now, a binary search tree is a great idea, but a binary search tree is only efficient if it's if it's balanced. If everything's off to one side, then we basically just have a very fancy, complicated linked list, and we've gained no efficiency whatsoever. So we're going to have, now we need them to be balanced. We know it's balanced if the height of the left branch is within like one level of the height of the right branch. Then we know we're getting efficiency. So we're going to have a piece of height information, an actual piece of data which is polymorphic in this case, it could be anything, and then a left tree and a right tree. Very simple data type definition, easy. So we need to insert, be able to insert into that tree, and that means, so we got a value x, we're going to pattern match on the tree we're inserting into, because we're not dealing with mutable data, it's immutable data, so we can't change the tree, but we can generate a new tree. But because it's immutable, in most cases when we're generating a new tree, most of the existing tree is going to be the same as the original. So the memory usage is not as bad as it seems at first glance. So if we insert into a empty tree, we're going to just get, it's going to have a height of 1, that value, and then 2 empty branches. Now, if we're inserting into a node, we have a height, we have the value there, left and right. We can put conditional guards on our pattern. So if we say when x equals v, well, we know we found the same value that's already in the tree. We don't need to add it. We can alias the name of that pattern to n, so we just return n. There's no changes needed whatsoever. Now, if the x value is less than that root value that we have there, now we're going to insert into the left tree. And to maintain the heights properly, we need to actually calculate, we need to recursively insert into that left branch, which we're doing. And then we're going to actually be able to calculate the new height of the root node, because we may be changing that. And so that's going to be the maximum of the height. And I'm just realizing, of course, I have forgotten to define a height function, because we can't just access that height value on an empty branch. So we're going to come up here, and I'm going to quickly define this. It's the simplest function you'll ever see. An empty branch, an empty tree, it obviously has a height of 0. A node is just that height. We don't need to worry about pattern matching the other values inside the node constructor, and it's just going to be the height. And we had to add 1 because, of course, whatever the maximum of those two branches is, so if one branch is 4 levels and the other branch is 2 levels, adding them into the node itself adds a level to it. So now we just have the H prime V L prime R. That's our new node if we're inserting. Now, of course, if we're now the only other case left is we want to insert into the right node. So we don't need any conditional guards because we already know what's going on just by process of elimination. use a little bit of copy and paste here. That feels like cheating, but so be it. I don't want this to run forever. So there's an insert. So if we can test this, we're going to use a special operator, that pipe and the greater than, that takes whatever's on the left-hand side and applies it to whatever the function on the right-hand side, which means we can chain together some operations really nicely. And we see exactly what we expect. So that 4 at the root, that has a height of 2 because it has 2 branches, one with 3, one with 5. Those each have a height of 1. We know this tree is balanced. We can write a test to find out if a tree is balanced very readily. Obviously, an empty tree is always going to be balanced. A node, though, we don't care about its height or its value. We only care about the left and the right, and only if the height of the left minus the height of the right, the absolute value of that is less than or equal to 1. Very easy. So if we check that previous tree, obviously it's still balanced. We're going to also look for the ability to get the minimum value from a tree. This pattern matching stuff should start to look pretty darn familiar, so I'm not going to explain that every time. If the minimum value, it's always the minimum value is going to be the leftmost value in the tree. So if the left branch is empty, then we've already found it. The current value is the minimum value in the tree. Otherwise, we only really care about that left branch, and we're going to call our function recursively on it. Same thing we can do for the max value is going to be the rightmost value in the tree. We know we found it, of course, if we actually have an empty right branch. There is nowhere further to go to the right. That's what I get for not editing quite right. So we have all these different things coming together. We also need to be able to delete from a tree. That actually depends on those min and max value functions, so very, very important. We're going to look for a value to delete, called x. Obviously, if we're deleting from an empty tree, we get an empty tree back. If we're deleting from a node where with empty branches, we get where we found that we get nothing back. We get an empty branch. If we are, and what we can do is, if we know that we can actually say, if we know that the left branch is empty when we've found the thing we want to, we could just make it the right value. There's no need to do anything further. Similarly, if we have instead of the left, the right node empty when x equals v, then we know we're just left with the left branch. Simple, easy peasy. Now, the trick is we have two non-empty branches, and we've found that the value we're looking for is left. So it has to be, it either isn't in the tree at all or it's in the left branch. We're going to have to delete from the left branch that value. So now we've got that branch with that value removed. We have to actually calculate a new height for the root node that we're going to construct. So that is going to be the larger height of the two, of the new left and the old right, plus 1 to accommodate the actual root node itself. And similarly, we're going to do something very similar when it goes the other way around. We'll copy and paste. Except this time we're modifying the right branch. Now, all we're left with is we have two non-empty branches, and we've actually found the value we want to remove. So in this case, we're actually going to have to pick a side, and I'm going to pick the left side just for the sake of it. We're going to find the biggest value on the left of the left branch and make that our new root node. But that means we need to remove that value from the left because it doesn't need to be there anymore. And that is going to be relatively simple. So we're going to delete the and that means that we're constructing a new node. We have to know how big it's going to be. So we're going to, again, calculate that information. Incidentally, this attaching heights, there's a few different ways to implement it. It's generally called an AVL tree. You can look it up. I never can remember the names of the two people that AVL tree is named after. Don't ask, I just don't remember. So now we can take a look, and if we were to delete 4, for instance, which is our root node, we end up with 3 being the root node, 5 being the new right node. Well, because that's where it was before anyway, so that's unchanged. Which makes sense, because if we look at our code in the case that we're dealing with, the right node doesn't get changed at all. Now, I did forget when I did that to add 1, which is why we saw a height of 1 for the root node. So if we try that again, now we see correctly that 3 node has a height of 2. Now, of course, the trick is it does have to be balanced. And the method of balancing a binary search tree is to rotate it. So we take, if we had a tree that was, like 5 as the root node, and then 4, and then 3, we'd pick the new root node to rotate it to the right. Our new root node would be the largest value on the left side, and then we would rebuild the tree around that pivot point. So So if we start with rotate left, just because I felt like it, obviously empty tree gets mapped to empty. If we're rotating a tree with nothing on the right hand side, with an empty right branch, then we just get that tree back. There's nothing to rotate to the left. But if there is, now we have to say our rotating to the left, it's going to be the minimum value on the right hand side is going to be our new root node, which means, of course, that our right hand side, that right hand branch, that has to have that minimum value removed from it. Otherwise, we're going to get duplicate values in our tree. So now we also know that we need to actually take that value, that v that was at the root, and move that into the left side. And that means we're going to have to construct a new node on the left as well. So that node is going to have a height that is basically the height of the left plus 1. Because we know we're going to take that existing left-hand node, that branch, and keep it entirely intact. And we're going to add something on top of it. So its height's going to increase by 1. And that is going to have as its root that old root node value left, and then it has no right. There's no right node to this. There's no right branch to it. So now our new height for the prime is going to be the height of these two new right and left branches plus 1. If we test this, we can see, now we knew this one, we have 4, we have 5, it's balanced, so rotating it is a bit odd because we don't need to balance it. But if we do that, we'll now see that we have 5 and 4 and 3. We've made ourselves a bad tree, but that's okay. This has just been, that was just for demonstration purposes, and we're not going to directly use those rotations. In fact, if we were really polishing this up, we'd probably put this in a tree, we'd probably put this in a module, make those, make it an abstract type, and that these rotate functions wouldn't be visible to the actual user of the module. So these rotation, you can see clearly it's basically just the same thing, but inverted. And that, again, is our balanced tree that's now been flipped on its side, and has 3, 4, 5 going off to the right. Next check is going to be, is the tree actually balanced? And fortunately, because that information sits in the data type, those heights, this doesn't have to be a recursive function at all. An empty tree, of course, is always going to be balanced. We can see in the other window, by the way, that's still running. It's still thinking about it. An empty tree is always balanced. A node otherwise, and we don't care about its height, or honestly its value. We only care about the left and right. And we're just going to check if the absolute value of the two heights. Just checking this. If the absolute value of the height, the left height versus the right height, are minus that. So if it's -2, you get 2. We're going to make sure that's less than or equal to 1. So now there's our balanced tree. If we say is balanced, we'd get true. But if we rotate it in either direction first, we'll get false, because we've now made ourselves a non-balanced tree. Without the balancing, all of this totally useless. So what we want to do now is find a way, is actually write a function that will balance a tree. Not check to see if it's balanced, but actually perform that balancing. Obviously, an empty tree is already balanced, so there's no need to change it at all. Similarly, if both are empty, it's already balanced. There's no need to do anything. Otherwise, now we have a little bit more difficult time. What we're going to do is we're actually going to balance the subtrees. So this is where the recursion comes in. And so now we have those two things balanced out. What we're going to check is we're going to build a new node. We're just going to call it n for the heck of it, with the height. We're going to calculate a new height. So this is the new node with the two subtrees balanced. That doesn't mean the whole thing's balanced though. So we're going to say if n is balanced now, then very simply we only need n. No need to do anything further. Otherwise, we're going to balance n. We're going to balance that new node that we created recursively. So pretty straightforward. So what I want to do is now go back to this. We built this balanced, but we then unbalanced it, and now we're going to try balancing it back out. Now clearly I've gotten into a an unbounded recursion situation because this is just sitting here. That's never going to complete. So what we need to do is figure out why that's happened. And really, when we take a look at that imbalanced tree, our right node our left node was balanced, it was empty. Our right node was also balanced. We basically reconstructed the same tree and then balanced it. And that's never going to complete. So what we really need to do is figure out which way it's imbalanced. So rather than check to see if it's balanced, we're going to say, if it's balanced, then just return it. That's fine. There's nothing wrong with that at all. But we now need to say, okay, if the height of L prime is less than the height of R prime. So if it's right biased, then I'm going to just skip down here a line to make this slightly easier to read. We're still going to balance it, again, recursively, but first we're going to rotate the whole thing, that whole tree, to the left. Otherwise, we know it must be left heavy. And we're going to rotate to the right. Oh. That was a silly mistake, but those happen. Fortunately, easily fixed. Now we get an immediate response. And that, again, 4 at the root, 3, 5 off to the sides. If we try a more complicated, we're not going to rotate this. We're going to actually start inserting some other values into it. And especially some sorted values, because sorted values going in without any kind of balancing happening, that's bad news. So now we can see we have 4 at the root, 3 off to the left, but then 5, 9, 6 off to 10, 11, 12. We could even make it worse by throwing a 13 in there. And that's a really badly balanced tree. But if we try actually balancing this, we now notice we have, in those heights, you can see it reflected in the heights. So if you look up above, the top height is at 7 levels. Every level that we have to increase our tree by, the efficiency is going down. Now we have gone from 7, so it would take 7 comparisons to find out if 13 is in that tree or not. Down to 4 comparisons, and the same amount of data. So we've actually almost halved the amount of work we'd have to do to check for membership in that tree. That's really, really important. We can now build some very simple functions that essentially insert or delete and then balance when they're done. So now we have those 2 functions. Now, let's try writing, we can use this as a set, and let's try rewriting to some in a little more sophisticated way. We use an inner function to hide some of the implementation details. Call it toSum prime, just for fun. And P is going to be our previously seen elements. And then we don't need to specify the target to this function because it already sees it from the outer function. It encloses that scope. So if we have an empty function, we haven't found anything. Now we're going to check. So we have the first and the element and the tail. So the complement C is target minus X. And if we also need to write a mem function to find out if something is in a binary tree, a balanced binary tree. So that's pretty easy too. Obviously, it's not it's not going to be in an empty tree. There's no chance of that, so we can return false very simply. Otherwise, we have a node. We don't care about the height in this case. We do care about the value when x equals v. Obviously, true. Otherwise, we don't care about the height. We don't care about the value. Care about the left. We don't care about the right. When x is less than v, then we're going to check for membership of that value in the left branch. Now, obviously, we know from here the only option left is it's going to be in the right branch or nowhere. Now we can continue with that toSum function. So if member, so mem is membership, is it an element of that? So if the complement is in our previously seen implement, so we're building up this list, we're actually looking backwards rather than forwards, then our complement and x is the return value. Otherwise, we're going to and we're going to recursively call our function toSum prime. We're going to actually add that x value to the previously seen elements and then check the rest of the list. And we're just going to call toSum prime with an empty tree to start with and the list of things we're looking for. Oh, that is a silly thing I did. I realize I do actually need to bind the v value there because we are using it. So now you'll note the other window still going. We're going to try something. We're going to try the simple example. Oh, I did that in the wrong place. Over here, and it should immediately find 2, 5. So we know it's working. So now let's try this hideously evil giant list and see what happens. It probably still won't find anything, but it should run much more quickly. Obviously 10 million, it's still a lot of work to do. It's a big tree to build in memory, but the good thing is we're dealing with log 2. So log 2 of 10 million. Log 2 of 10 million is a really small number. A comparatively small number anyway. So let's just quickly see if we can calculate that. So we actually don't have to go down to. So we're really only going like 30-ish levels down the tree. It's still thinking, but obviously we've had time to write an entire self-balancing binary tree implementation on, well, this is still considering. Well, this is still thinking. But I'm bored at this point, so I think I may have been too ambitious. Let's try a smaller sample size. Let's try 100,000, and we're going to set it up in both. And we're going to kick these off one right after the other, and let's see what happens. This is a very, very boring race between the really naive and the slightly less naive solution to this problem.